Next report. Tall Tales, Interrogating the Typology of the Tall Building. Speaker, Mark Sarkisian. Mark Sarkisian realized innovative structural engineering solutions for over 100 major buildings around the world. He is director of Skidmore, Owings and Merrill. Mark holds 4 US patents for high-performance seismic structural mechanisms designed to protect buildings in areas of high seismicity, and has additional patents pending for seismic and environmentally responsible structural systems. He has recently written a book entitled Designing Tall Buildings, Structure as Architecture. Please, your report.
Thank you. So I'd like to start by talking about a simple move, simple programmatic move to an existing tall building. This is the Willis Tower in Chicago, formerly known as the Sears Tower. And you know, we think about tall buildings and the effects on cities and on developments, but one of the things I think we should consider is the change in typology over time and what small programmatic changes may mean to the use of a very tall building. So in this idea was to introduce a way to, I'll say, re-experience the observation deck of the Sears Tower. And the idea was to create a module that could be moved outwardly and then moved back to allow window washing and actually to allow the structure to maintain its original design intent. So these modules are actually quite small. There's a steel frame. There's a triple glazed glass unit that is inserted and hung from the frame. But the idea is that in some ways it's a temporary solution or a temporary idea to creating a different experience for people at the observation deck level. On the west facade only, on the tower, the reason for this is because of the straight shot of the exterior wall from top to bottom. There are no setbacks below this western face. And the concept was to allow people to experience the Sears Tower in a much different way, to be almost on the roof level without any barrier. And the experience would be one that was different and one that was, I'll say, integrated with the surroundings. Nighttime and daytime having different experiences. But a very simple idea, a very simple move to create a different experience. And what's happened in this case is that almost immediately after the ledge was installed, as we call it, there were 10 times the amount of people that were interested in visiting the space at the observation deck level. So I leave you with this thought on this project. It's about, I suppose, daring ideas, and I actually would argue that when we think about tall buildings, we should think about spaces, and we should think about what brings people to those buildings. And I think that we've done a lot of buildings that, in fact, miss opportunities, and this perhaps is a small way of reminding us what it might mean to create simple moves, simple, important moves to the typology of these tall buildings. You know, when we think about structures, I think we're restricting ourselves far too much, and I think that the work that we're considering at SOM is work that looks at structures in a way that are more at a finer scale, perhaps more at a mesh type scale than a beam and column or a large mega scale. The idea that elements are purely in tension or compression, they're not bending, and with that response to gravity and wind loads and seismic loads, you in fact come up with the very most optimal and the least amount of material in the structure. It's about a typology. It's about understanding force flow, and it's about optimizing the structure to respond to that force flow, whether it's gravity loads or lateral loads. People have talked, and we have looked, and we're looking very carefully at genetics in terms of the random association with material and boundary conditions, whether it's the geometry of the tower, both plan and elevation, whether it's fixed conditions at the base, whether it's change in geometry over the height of the building. We're looking for the most optimal way to combine the applied loads against and comparing against the minimal amount of material. So freeform, you know, I think we're on the verge of defining structures that are far less rigorous than they were in the past, and perhaps solutions that will be far more beautiful as we go forward. I want to talk about towers that have limited program. The idea that we introduce these objects, these structures, in a way that perhaps create energy, manage energy, and in this case, we called it the Oasis Generator, a structure that could use concrete in the center. It could erode as we got toward the top of the building. It could change shape, in this case 9 meters in diameter at the base and 30 meters at the top, using the principles of tension on the outside and compression on the inside to resist overturning. And, you know, a concept of moving people from bottom to top, perhaps in modules that move around the perimeter of the building. It uses, again, the idea of least material and the idea that there is limited programs. So the top of the building is essentially where all these spaces would exist. Structurally, a very efficient idea. The idea that as forces flow through from top to bottom in the center core, there's greater density. We use high-strength cables around the perimeter of the tower to resist the overturning. And we combine these two ideas in the purest sense of compression and tension to reduce the amount of materials. The other idea is to use the evacuated tube systems that could be attached to the inner core to generate and capture heat, and then in turn use that the water that is being heated within that system to desalinate water that would be coming from the neighboring environment. This is a site in Dubai, which the concept was originally developed for. The other idea is as air moves through the center of this shaft, turbines could be used to generate electricity. So beyond the limited program, the idea would be that in fact it would provide energy, and in this case, desalinated water. You know, our structures are filled with opportunities. I'm convinced that as far as exterior wall systems, we're only scratching at the surface. There's a huge missed opportunity, in my view, as to what we can do to capture energy from the sun, perhaps in this case, in this concept, use winds that are affecting the tower in a positive way. So the idea perhaps is to introduce openings along the height of the tower, but not just to allow winds to pass through, but an idea that uses a technology that we see all the time, and that's the use of airfoils, whether it's automobiles or airplanes. We know that there's lift and drag that is associated with airfoils. And we know that the flow around the towers are one that we can actually take advantage of. And perhaps we introduce these openings, and in these openings we have, instead of just pass-throughs and turbines, we have foils. And these foils can be used to actually provide resistance. So applied loads, when engineered properly on the leeward side, would form uplifts that would counteract the overturning, using the passive characteristics of the wind to actually develop forces within the structures to create resistance. And perhaps reducing the diameter of these openings as we pass through the tower to increase velocity, increase the amount of energy, the power that's generated by wind turbines that could be created within. Our cities are in trouble. And we talk about tall buildings, the urban habitat. I think one of the things that we're missing, I'm a structural engineer, but I work in cities, I've lived in cities. We're missing the opportunity of the urban habitat. And for us, I think there's a huge opportunity to develop ideas that parametrically model cities in a way that look at the environment. So when we talk about cities, when we talk about structures, I see that there really are primarily three components when we talk about building efficiency. There's the structure, there's the architecture, and then there's building services. Every built environment has got structure. So what we've been looking at is looking at parametric models that take the tower and try to come up with early ideas about what it might mean to change certain parameters in the structure and see what it means in terms of efficiency. It's taking advantage of the occupied space. So as an example, the Burj Khalifa. You've seen this before, the floor plan. This is the occupied area overall, the structure, the services. Now, if we look at this in a way that allows us to come up with limits, how tall can we build? This is I'll call it a typology model that looks at building height and it looks at components, the structure, building services, and then what's most important, I think, at least in the early stages of design, forget about aesthetics, it's leasable space. What is the quality of the space? What is the value of the space? So I'm just going to look at the left side of this graph because there's a lot of things going on. But in our towers, if we target the minimum allowable leasable floor space that we'll accept for design, let's say it's 70%. If we look at the structure, we assume a certain amount of material strength. Perhaps the building is an area of high seismicity. All this means is that there's demand on the structure that creates structural size. It's not a beam and a column and a wall. It's a material, and based on the allowable strength of that material, there is a size. There's an area that is there to take up the space. So we can look at the structure over the height. So this is various heights of buildings. The blue line that's solid is leasable area at the ground floor. So if you look at the intersection between the height and the 70% efficiency, it means that for this building that's got 10,000 psi concrete in a high seismic zone, you can basically build this building so that the ground floor has a leasable amount of space of 70%, and you can build it to 170 stories. If you look at the average area, if you say, okay, fine, I'll accept lower percentage of area at the base, but I'll take an average of 70% over the height of the building. I can build this building to 270 stories tall. It's a way to create a metric, a starting point that looks at efficiency. Building services. I mean, in terms of the floor plan of the Burj, it's approximately 15% of the area. It may vary over the height of the building, but it's a starting point. And you can look at things like loads and applied loads and so forth that also affect the structural size. So in modeling this, I think what's important is what does it mean to change shape? What does it mean to increase the height? So in this example, we're changing the height of the building. We've set a minimum floor efficiency of 75% with an ideal floor efficiency of 85%. The gross area is changing, and you can see that the efficiency of the least efficient floor is changing. As the building gets taller, the demand is greater, the structure is taking up more space. It's taking up more space. And if I change the width, it's also having an effect. Red means that I'm below my minimum threshold. Green is good, that I've met my minimum threshold. So this is a way to take cities at the very early stages of design and parametrically model them so that we understand what we're getting ourselves into. So we can look at different things like concrete strength. So with higher strength concrete, the poorer areas tend to disappear. When we look at steel, perhaps the section sizes are smaller. We look at higher demands like wind or seismic, we see that the red areas increase. Now you can also look at, I'll say, a material of the future. Other materials. What does that mean? It may mean that we've got super high strength steel or concrete, or we're treating it in a way that that is far more efficient in terms of its, could be compressive strength. In this case, where we're modeling it to be a sort of a super high strength material that might be related to concrete. So, the day we build structures, it takes 20 years typically before the operation catches up with the carbon that's emitted for the first day that we build the structure. So it's important that when we build our structures, we think about the material, the construction, and the damage that structure might see. So the idea is that over the life of that building, if we have enhanced seismic systems, for instance, the damage due to seismicity could be reduced, and so would the carbon. What this idea does, and it links to that program, is that very early on, if we have steel or concrete, we know the number of stories and so forth, it looks at a database of projects that we've designed that for a certain number of stories in a certain environment, we can expect a certain amount of structural steel or reinforced concrete in the building, getting to the material, the construction, and probabilistic damage that's based on the structural system. Again, it's looking at the environment relative to that parametric model. The last thing I want to say is that I think that there's a wide open opportunity here about freedom of thought about structures and architecture. And I think that the idea of emergence is one that's really important. It's the idea that individual common elements are far more powerful when they're working together than when they act separately. And we see it in things like birds in flight. We see it in cities. The idea that people living together, interacting like we are today, is far more powerful than we would be if we were on our own. So, what does it mean? Amsterdam did a study. They tracked the movements of people within the city over time. They had tracking devices, GPS tracking devices. And the interesting thing is that the people moved where they were told. They moved based on the rules of walkway systems and roadway systems within the city. My argument is, should we be bound by the column lines and beam lines that we draw for our structures, or we should be looking at the spaces in between? Are we saying that the spaces in between in that city are not effective? And I think it's the same idea for our structures and how we think about material and the use of material. There's interactive art that, in this case, in Rotterdam, it's called the D4 project. The entire community participated in this project where moods were entered each day. And red, I forget exactly what it is, but red may be anger, yellow may be happiness, blue may be sadness. And people could interact, emergence, the idea of people working together, in a way that they understand the mood during that day. And if you didn't participate, you understood the mood of others that were participating. You can control this. This is not something that just forms by just purely by nature. You can change the boundary conditions. David Nash in Ash Dome he changed the boundary conditions by putting weights on these trees to create this dome, create this new form that was imposed with a superimposed idea. It's about alignment of material, and it's about forms that we can't quite rationalize initially. It's about where material is needed based on forces, based on support conditions. It's based on thinking about structures three-dimensionally, volumetrically, rather than on surfaces. So how many of us think about the structure through the space rather than just at the perimeter of the space? So I think the solutions are wide open, beautiful. It's about the material that you need, not the material that you just place there because it's something that we do in construction. It's about the erosion of material. It's about using concrete in a way that's more fluid. It's about support conditions at the base of a tower. It's about loads that are applied, and it's about the flow that happens, red being the highest areas of flow and blue the least. And then there's a rational solution that may come from it in terms of the structure and the architecture. And last thing I'll say is, I think it's about flow. And one of the things that we're looking at is the placement of material and structures that perhaps can be altered over time. And the best example I can give you is a state change. Water that's changed to a solid. There's a change in properties that can happen, and what we're looking at is using different means to perhaps change the characteristics.
Sarkisian, you have 2 minutes.
Yeah, thank you. To change the characteristics, to use the absolute least material. So gravity is something that we can't, at least from what I can understand, we can't change. But wind and seismic forces and other forces come and go. So the idea is to move material within systems and perhaps change material properties to resist those forces. So that's what I have. Thank you.
Thank you very much for your excellent presentation. We're going to have just one question. Okay.
Hi, good afternoon. Uncannily, there was one architect in India who said something very similar to what you talked about open spaces, and he'd said that instead of trying to infuse and hard-code what people should do in open spaces, you should just kind of design the open spaces and let people infuse the character in it. In the context of what you had said regarding this, are our current design processes that we follow for any of the buildings, can they achieve this kind of an objective where we're looking at this flexibility of spaces for people to do as they would with it?
Are you referring back to the original example that I gave?
Yeah, the example that you'd given, that where we are hard coding the cities into where they're being told to walk, and hard coding, regarding that. So the architect that in question had also said something very similar. He said instead of hard coding spaces into trying to tell people what they should do there, you should just design the spaces and let people decide what they should do with those spaces.
Yes.
So in the standard design process in the design process that we follow, even within the integrated design process that we do follow, is such a result feasible, or do we need to change the way we think about
design? Here's what I think. I think that we impose the rules on ourselves in terms of our engineering and our architecture, and I think that example of the city is one that really is a definition that we've imposed. So when we talk about space, I really believe that we should think about structures, for one, as volumes, and those volumes we can modify. We can modify them in a way so that the first thing our junior engineers and our architects don't do is sit down and draw a column line. Okay, so the idea is to open this, and I'll say that we're not quite there yet because we've got to build this stuff. All right, so conceptually these are great ideas, but we have to come up with a way to rationalize them. So we're getting there, I think, on material, especially a material like concrete, where there is an opportunity to be much freer about the form and the response and what the final geometry might be. And that can be done through things like fabric forming and formwork systems that are far less rigid than we think about today in building our buildings. So I don't think we're quite there yet, but I think that it's certainly an exciting thing to think about and try to implement.
Thank you. Thank you. Our next report.